think it'll be useful if we start off with looking at just what happens during a pumping test in a conceptual overview. So if this feature over here is our well, and we start pumping, then after a short time we'll have something that looks like this. There'll be a bit of drawdown in the well, and we've started pumping at constant rate, and there's also some drawdown in the aquifer. So if we imagine what's happening is that the well here is screened in a confined aquifer. Then after we've been pumping for a little while, we've pumped out a certain volume of water. And that volume of water came from storage down here in this aquifer. And the way we're able to get it out of storage is by dropping the pressure in the aquifer by this amount. So we've depressurized the aquifer out to this far, and the pressure distribution that the well has caused is shown here by this curve. Okay, so we do this some more, we pump some more, and the drawdown in the well increases, and we depressurize more of the aquifer, and we get out an even bigger volume of water. That water is removed from storage. Okay, so to get an idea about what's going on, we should go back and refresh our memory about this term storativity. So remember, we had storativity, and we said that was the volume that was recovered from storage, released from storage, per unit area of aquifer per decrease in head. Okay, so this is the water that was released from storage here. And if we say, well, the water released from storage is equal to the storativity times the area that's been affected times the drawdown. And now we'll think of this drawdown as an average. We see over here from this profile that the drawdown changes with distance. But if we just write it over here as an average, then we get this nice concept that the volume that's been recovered out of the aquifer is equal to the storativity times the area that we've affected times the average drawdown. And the area that's affected under these ideal conditions, this is a radius of influence here, and we imagine then that it's revolved around the well, and that gives us a circular area. And so the volume that's been recovered is the storativity times pi radius of influence squared times the average drawdown. Okay, that's how we get this volume that's been removed from storage. Okay, so let's take this one step further. We say, well, how does that volume that's been removed from storage change with time? And if we do that, we say, well, the volume that's removed from storage with over a unit of time, so this will be like a derivative, that actually we know is constant here because that's the pumping rate, that's Q. And Q then will be equal to, well, S is constant, pi is constant, and we'll just assume that the radius of influence is changing slowly. So we'll write that like this, Ri squared times the change in head with time. Okay, so what this allows us to do is get a handle on how rapidly the head is dropping as a function of time. Okay, and let's just say this is approximately equal to it. There would also be another term that involves the derivative of this guy, but we're not going to include that. We're going to assume that that's small for now. And so what this allows us to do is take a look here. And so what it says is that the flow rate, that's constant, that's constant, that's constant. And so the rate of change of the head, this is how rapidly the head is dropping, that is going to equal, Well, that's going to be decreasing as the radius of influence is increasing. Okay, so what that means is that as we start to pump this well, initially the head drop will be rapid, but then as the radius of influence spreads, the rate at which the head drop progresses, the rate at which the average head drop is changing, will become less and less. We always will have to have more head drop, so the head will have to continue to drop with time so long as we're removing water from storage, but the rate at which it happens will become less and less. So if we continue to pump, we see that it's spreading out, but with each successive time, the amount that the head drop is diminishing. So if we plot the head in the well, then because of the way this is working, we expect to have something that looks like this. Initially, this rate of drop is fast, but then as we pump longer and longer, the rate at which it drops diminishes. So this slope is getting flatter and flatter. It'll never go to zero so long as we're removing water from storage, but it can get flatter and flatter. Okay, so that's what happens. That's how we can get water out of the well, assuming that this is a confined aquifer. It's releasing it from storage and we're pumping it out of the ground, and the rate at which, or the region that's affected, propagates out and gets to be larger and larger. Okay, so that's what happens when we pump. Then we shut the pump off and the water level starts to recover. Okay, so let me erase all this stuff. So we pumped it down and we shut the pump off. And well, actually, I guess before we do that, let's take a look at the drawdown. This is the head in the well, and the drawdown is the difference between the static water level and the head in the well. And so it's just going to be the mirror image of the head in the well. The drawdown increases with time, and then its rate of increase gets less and less. Okay, so now we've stopped pumping and let the aquifer recover. Well, what happens then is that the water level in the well rises, and in order to do that, we have this region in the well. Initially, it doesn't have water in it, and so we have to have a little bit of flow go into the well to provide this water to fill up the well. So we have a very slight gradient here, but it's a very slow flow. It's not very much water, so it's a very slight gradient. So that the head profile goes from being a fairly steep gradient here to being quite a flat gradient, and the profile comes out looks like this. And then when we get out a ways away from the well, what we see is that this was the head out here when we stopped pumping, and that out a ways away from the well, the drawdown can continue to decrease even though we stopped pumping at the well. It's increasing, or the head in the well is increasing, the water level is rising, so the drawdown is increasing, or the head is increasing, the drawdown is decreasing, and that's what's happening here. But out here, just the opposite is happening. Okay, so we keep on going with recovery. The water level rises some more, and here it's rising, here it's rising, but we have way out here the water level continues to fall by just a little bit. Okay, and that continues on until we have the well return to the initial conditions. Okay, so I think actually if we take a step back, this is a little bit peculiar that the water level is continuing to drop in this second step. Let's go back. Oops. In the second step, right? So that's a little bit peculiar, but I think that it makes sense, because in order to do this, in order for the water to fill up the well, and in order for the head to increase, we have to have water. Well, that's going to require some water. So where is that coming from? Well, it's coming from this right here. So we drop the water here, we drop the head, and we raise the head here. So we continue to have flow coming in like this, where we're releasing water from storage and we're adding it to storage here, even after pumping has stopped. And then that continues on, and the well eventually recovers. And so we have the head in the well rising like this, and the rate at which it rises is fast at first, and then it levels out. And the drawdown is just the mirror image of that. So we have these two main periods where we pump and we have the head drop and then recover, and the head rises and approaches the initial heads. And so that gives us two conditions where we can analyze the results: the conditions during pumping and the conditions during recovery. Both of these are responding to the formation properties, the hydraulic conductivity and the storage. So they depend on those guys, and they also depend, of course, on the well thickness and the pumping rate. And then what this looks like, the drawdown, it depends. Well, the drawdown in the well is going to just obviously depend on that. That'll just depend on one thing, where you are at the well. But the drawdown out here will depend on how far away you are from the well. So the further away you are, the less the drawdown is going to be in general. But there still will be drawdown, even way out here. There'll still be drawdown. You'll still get an effect, and that is potentially at least an effect, a signal that you could measure and analyze. Okay, so that's the basic concept. Now, one thing that will happen is that wells are not going to be ideal. And so this shows a non-ideal condition. The drawdown, this is, I guess, a snapshot during the test that we saw earlier. And this line here is what we might imagine is happening under ideal conditions. But if the well has some low permeability material that we'll call a well skin right around the well, and this is a common thing actually that occurs as a result of the drilling process, then that well skin has hydraulic conductivity that's lower than the formation. So it's kind of clogging things up. And as a result of that lower hydraulic conductivity, the head gradient in this skin layer is steeper than what it would be if the skin was not there. And so that's the gradient, that's the slope of the head with the radial distance that we would expect under ideal conditions, but actually the slope is like this. So it's much steeper. And the result of that is that the head that we see in the well is here. So that's the head in the well. That actually occurs. What we would expect under ideal conditions is this. So we've got a lower head and more drawdown that results from this well skin effect. Okay? So that's an important concept. What it means is that when we're measuring the water levels in the well, they're going to respond to the properties of the formation, K and B and S. But they'll also respond to the properties right around the well, this well skin. And so we might have this additional drawdown that occurs as a result. The consequence of that is that in the well, the head, as a function of time, might look like that under ideal conditions, but as a result of a well skin, we might end up with this dashed line. So there's just additional drawdown that occurs throughout the test as a result of the well skin. Now, in contrast to that, out here in a monitoring well, we have a drawdown that occurs. This drawdown is occurring as a result of the pumping rate from the well, and it's not really affected by this well skin, right? Because this is the profile that would occur in the absence of the well skin, and this one here is what would occur with the well skin. So the effect is really right here at the well. And what that means is that there can be problems with analyzing the data from a well, from the pumping well, as a result of the skin. But if we step away from the pumping well and get data from the monitoring well, that those data will not be as affected by well skin. So that's going to be an important reason for using the monitoring well as a source of data for analyzing this signal that allows us to determine the properties of the aquifer. Okay, so another important aspect is that in order to do the analysis, we have to have measurements of the hydraulic head or the water level in a well. And if we stress the well really hard and make measurements over just a short time period, then we can probably get by with just treating those measurements at face value. But if we're going to make measurements for a longer period, then what we need to do is be able what we need to do is recognize that the heads in the well may be changing as a result of other things in addition to the pumping that we're doing. And so we need to take those into consideration, because if the heads are dropping, for example, as a result of some other process, and we assume that they're dropping as a result of pumping from the well, then we'll be off in our interpretation. So what we need to do is take a look at, well, first of all, what are some of the things that might cause the head to change in a well, and what is happening in, say, for example, to the wells around here. So I went and got some data from the USGS, and if you go and take a look at this place, the National Groundwater Monitoring Network, the USGS has a set of wells over the US, and they're shown here, where they're monitoring the heads and the data are readily available. If you look at the area the wells in our area, there are not many, but there are some. And one of them, it's hard for me to see right now, but it's right around in there, is in the general vicinity of Clemson. It's in similar rocks. And so that's this well here. And I went and got some of the data over the last few years to just take a look at what the head in this well is doing. And so it's these lines here go from 1 June to the next June. So this is over several years, starting with 2009. And what you see is that the heads are moving around through the year. The scale here is in feet. So during 2009 to 2010, the head variation in this well 233 is a bit over 4 feet. It's almost 5 feet of variation. And it looks like if this is June, it looks like maybe July or August it reaches a minimum, and then it's rising later on, and then this is probably, I don't know, February, I guess, and then it falls during this time period. This is probably February to about November. And then this is actually a fairly short period of rise relative to the year before. And then it falls, and then it rises and falls. So during each year, it's falling, and then it's got a period of rise, and it's falling again. So for these kinds of things, this is called a well hydrograph. And when this hydrograph is falling, we call it a recession. And when it's rising, the water level rising in a well is a result of recharge. So during these years, from 2009 to 2011, we see periods of recharge and periods of recession. Water level is dropping and falling, or dropping and rising. And then we have something a little bit different happening during 2012 and 2013. here's dropping, we see it rise, and we would expect it to be dropping in here. But last summer, we had some very big, unusual rainstorms. And as a result of that, you can see there's one right there, and there's another one, and this is another one right in here. And so these rainstorms cause there to be more recharge during this year than typically occur. Okay, but this is the general pattern that's going on. And so what I did was to go in and plot the slopes of these lines. And so this curve here is minus 3 millimeters of drop per day. And this curve here is plus 12 millimeters of rise per day. So in this well, the typical response is it's dropping for a while and it's rising in some cases. And these are kind of ballpark slopes over which this is happening. So what you would expect if you were going to go and conduct a test in this well is that at any given time, the water level is probably changing by something in this ballpark. And it may be falling, it may be rising, you don't really know. And so if you conduct a test and the test is, say, several days long, and the pumping well is quite a ways away, and the signal that you're expecting at the well where you're observing is going to be small, then the signal may be similar to this magnitude. And so the rate at which the water levels are changing in kind of a background or ambient way is something that you need to take into consideration. So if we look at this same signal at the well in Clemson, this is at the lower well field in the bottoms, or in lower well field in the botanical gardens. Then we've got a transducer that looks like this, and it's hanging in the well. And so our well is here, there's a water level, and we've got a wire that hangs this transducer down here, and it measures the water pressure like that, and records it internally. And let's see, it's set up like this. So there's also the barometric pressure up here, and this well, or this transducer, is sealed, and so it's measuring the total pressure, and that's a result of the depth of the water and the barometric pressure that's pushing down on it. So when you use something like this, you have to also have another transducer up here that's measuring the barometric pressure, because what happens is the water level changes, the water level rises like that. That causes this to measure an increase. And at the same time, the barometric pressure is also rising or falling. And so to separate out the two, the change in the water level from the barometric pressure, you have to measure the barometric pressure separately. So that's what we've done. And you'll use one of these transducers to characterize the water levels in the well. And so you'll need to also have the measurements from the second one that's measuring the barometric change. And here is an example from that time period last summer, when during June here, this is starting in June and going into July, and you can see that we've got this period of recession where the water levels are dropping at roughly a uniform rate. This scale here is in meters, and so it's dropping at roughly a uniform rate until this period right there. And see that spike? That's a rainstorm. So the rainstorm causes the water level to rise rapidly and fall in the well, and there's a net increase in the water level. So if we go from there right to there, the water level rises and falls, and then there's that residual increase. And then during this rainstorm, it goes from there to there, rises and falls with a net increase. And then there's a continued increase after the rainstorm. Okay, so this is pretty clearly a period of recharge, and this is clearly a period of recession. So we can get an idea of what's going on here from the slope. This interval here is 10 days, and this is in meters. So the slope is approximately 1 centimeter per day during this recession period, and it's even steeper than this during the recharge period. So the message here is that if you're conducting a test during this recession period, the water level is falling, and if you have some big changes in the water level, if you're measuring 1 meter of change of water level over an hour, then this probably won't matter too much. But if you're having small changes over long periods, this may matter, and you should take this into account. And what you see is that during this recession period, during this whole period, we can characterize this effect really quite well by assuming that it's just linear and that it's dropping at that rate. So what that allows us to do is fit a line to this data and then take that linear fall in head and just simply subtract that off of the data that is happening during our tests. So this is something that is often done, and for pumping tests done at a professional level, you really need to take this into account to have credible data. So we'll measure this and show you how to make these corrections for the long-term pumping test in particular. Okay, actually, I guess also let me just point this out, that another thing that we can get out of this, let me just erase this, is that if you're conducting a pumping test and you're interested in very accurate changes in water level or changes in head that result from pumping, and you have a big rainstorm, then I think that, I mean, if you started your pumping test right here, you could have characterized the ambient effect, and you see that, well, it's rising like that, so I'm going to take that into account. But then you have a big rainstorm, and you see that that rainstorm can really raise havoc with the hydraulic heads. And if that's the case, it makes the analysis of the pumping test really very difficult. So that's something that you should keep in mind, that as you conduct these tests, you probably want to watch the forecast and pick a period when you don't have a big rainstorm. Okay, so we're going to conduct several pumping tests during field camp. This is an important test for hydrogeologists. It's really the best way of characterizing the properties of an aquifer. And so here's an overview of what you'll do. So start off, you want to plan the test. And this will involve making a map of the site. You need to know where the wells are, if there are some streams, other features in the vicinity. And you need to then figure out, well, how long am I going to pump? And to some extent, this is going to depend on what you want to determine, but it also is going to depend on just the logistics. During our course, we'll have a certain interval of time that we're going to be able to do a long-term pumping test. And also when you're on the job, time is money, and there'll be a certain budget for the test, and that will make the test limited to a certain time period. Okay, so you've got to come up with a determination of how long you're going to go, and then you have to determine how rapidly you're going to pump. And we saw that there are consequences of pumping and causing too much drawdown at a well. You might have the pump go dry. That would be bad. But at the same time, you're going to need to have a signal that you can measure. So you want to create as much drawdown as you can, but not too much. Okay? So what you need to do is know how long you're going to pump, and then you have to have some way to anticipate how the drawdown is going to develop during this pumping test. And so you have to have some preliminary estimates of the aquifer properties, and then have a way of forecasting how rapidly the drawdown is going to occur. That'll allow you to estimate what the pumping rate should be. And then you're going to plan out where the monitoring will be done. There'll be a set of monitoring wells, and you'll plan out which ones you're going to use, and also come up with an estimate of how often the measurements will be made. So that's part of your plan. And then the preliminary measurements, well, we just saw that you should have some background measurements of the change in head. So ideally, you would have a transducer in the wells, or you would go and measure the heads by hand for a period of time at least as long as the test, and probably more like 10 times as long, so you can characterize what the ambient behavior of the aquifer is, and that'll allow you to then be able to extrapolate it with some degree of confidence. If you have something that's going to change the ambient trend, like a big rainfall, then all bets are off. But if you have this background data, then you can extrapolate that out and use that to correct the data. And so this is something that has to happen before the test. So this requires some planning up front to make sure you have these data before you start. And then you may have to install a pump. Some wells have pumps in them already, but often they don't, particularly if this is a new site where you're working. So you need to install a pump, and you need to have some power source to power the pump, and you need to be able to set up what the pumping rate of the pump is. And in some cases, pumps can have the ability to adjust the rate, and so you need to dial in the rate that you want to use. And then the test itself, that will involve measuring the hydraulic heads at wells, at the pumping well, at the monitoring wells. And there will be two options for that. One will be to use a data logger attached to a transducer, so that can measure the heads or the pressures in the wells automatically. But what we'll do is, and what I would actually urge you to do in all cases, is to measure the heads in the wells manually, in addition to measuring them automatically with a transducer and a data logger. So we'll do this, and this will be the data that we'll analyze primarily, is the manual water level measurements. If you're doing this professionally, you'll probably have these data logging transducers, and that will give you much more data than you could measure by hand. But in any case, even if you're using those, you still want to make measurements manually. What you'll find is these data logging transducers are great so long as they work. But with any kind of electronic instrumentation, you need to have some backup, and you need to be able to verify that they're working correctly. So we'll always want to make measurements manually, and then we'll also make them with a data logger if we happen to have one. Also, as you're doing the test, you should verify the flow rate. We want the flow rate to be constant for this particular test. It may be, but because we're using equipment that is, it's real equipment that works in the real world, and pumping at a constant rate is not something that you can ensure. So because we're assuming that the rate is constant, we need to verify that that's happening. So we do the test, and then we have data, and the next step is to analyze the data. The way that this will be done is to plot the data up, and then we'll have a mathematical function or some kind of an analysis that will be a prediction of the data. So it'll be a mathematical version of the well and the aquifer. And so we'll use that, and it'll predict the drawdown, or it'll predict the data, the drawdown and the flow rate. And then we'll adjust the parameters so that the results of the function fit the data as best we can. So that's a curve fitting approach. And when we're done, we have a fit to the data that's as good as possible, and we have a set of parameters that is responsible for that fit. And that'll be the best estimate that we have for the parameters in the aquifer. And then once we're done with that, we compile our results, we describe what we did, we put the results in a table, and we put that all together in a report. Okay, so here's what the field work looks like. This is a well pump here, This is a 4-inch diameter pump, and it will go into a 4-inch well as well as a 6-inch well. It's powered by either 110 or 220, or actually I guess they're calling it 250 volt right now. So it has an electrical cable that's right here going down to it, and it has a hose that brings the water back up. So this pump is lowered down into the well and will typically then hook up a flow meter to the well. That's a flow meter right there. And then this is an overview of the site. So the pumping well is here, there, and the hose comes up and goes around like that and then goes through this flow meter. And then there's some monitoring wells here. There's one, and there's one. And so the people at the monitoring wells are using this water depth tape here to measure the depth to the water, and that will be used to calculate the hydraulic head. And somebody will also be monitoring the head in the well right here to make sure that the drawdown does not get down to the well. And also we'll analyze the head in the well and see how well that signal, see what kind of information that signal gives us. But it'll be the signals from these guys, these monitoring wells, that'll be the most important signals during our analysis.